Hi everyone, hope you're all getting on well. It's now time for our next lesson where we're going to be looking at equivalent dose and also equivalent dose rate. So, learning intention for today to define the concept of radiation weighting and equivalent dose, to explore the equivalent dose rate. So hopefully by the end of the lesson you'll be able to define the term equivalent dose. You'll be able to state a relationship linking absorbed dose to equivalent dose. You'll be able to solve problems involving equivalent dose, and you'll also be able to solve problems relating to equivalent dose rate. Right, revision to start off with, as always. Last time we were here, we looked at absorbed dose. So let's have a little reminder as to what absorbed dose was. So absorbed dose is the amount of energy absorbed by each kilogram of tissue. It's a living tissue, isn't the kind of tissue you blow your nose into. It's a living tissue. Absorbed dose is measured in units called grays, as I said before, abbreviated to capital G, small y. So here's our equation for absorbed dose. D, absorbed dose, measured in grays, is equal to E, energy, measured in joules, divided by M, mass, measured in kilograms. So that's D equals E over M, or absorbed dose equals energy divided by mass. So equivalent dose then. What is equivalent dose? Well, it's important to remember that not all radiations or types of nuclear radiation are equal. Sometimes some of the types of radiation you come across are more harmful than others. A good example of this might be, for instance, alpha. Alpha tends to be more harmful than others, although we're fortunate in that it can't travel as far through air. So it's important to bear this in mind. So to know if someone's at risk, it's not enough just to know how much energy they've absorbed from whatever radiation they have absorbed. It's important also to take into account the type of radiation that they've absorbed. And this is where equivalent dose comes in, and that is essentially what equivalent dose is. It helps us to take into account what type of radiation has been absorbed. So equivalent dose is measured in these units called sieverts, and that is abbreviated to capital S, small v. Radiation weighting, and this is how we differentiate between different types of radiation. So we have different radiation weighting factors, and we'll assign these to different types of radiation depending on how harmful they are. So if a type of radiation is more harmful, it'll tend to have a higher radiation weighting factor. So for example, we've got gamma here, has a radiation weighting factor of 1. We have beta, which also has a radiation weighting factor of 1. However, we've got alpha, which has a radiation weighting factor of 20. Now, what does that mean? Well, basically what that means is that alpha particles are 20 times more harmful than beta particles or gamma rays. So here's our equation for equivalent dose. So we have H here, which is the symbol for equivalent dose, H being equivalent dose measured in sieverts. D is our absorbed dose measured in grays. WR, as we saw in the previous slide, is our radiation weighting factor. Now it's important just to point out that the radiation weighting factor doesn't actually have a unit. It's just a factor, so it's just a number that we put in there. It's a bit like when we looked at frequency earlier in the unit, and you were looking at the number of waves that pass a point, or when we looked at activity and you were looking at the number of decays that were happening every second. It's just the number of things that were happening. In this case, it's just a factor, so it's just something that we're multiplying it by to take into account how harmful it is. So, first worked example for today. A tissue sample of mass 2.5 kilograms absorbs 3,200 joules of energy from a radioactive source emitting alpha particles. So A, we're going to calculate the absorbed dose, and then B, we're going to calculate the equivalent dose. So the first thing we'll do is I'm just going to split this page in two, and on the first side here we're going to attempt part A. So first thing we do, hopefully you're way ahead of me, as always, we're going to write down our shopping list. Now let's just highlight the important information that we've got in our question here. So we've got the mass is 2.5 kilograms. We have 3,200 joules of energy. And then from part A, it's asking us to calculate the absorbed dose. So let's note these things down in our shopping list. Next, we can gain our first mark. We pop in our equation. So D is equal to E divided by M. That goes back to our revision slide, or what we covered yesterday. Second mark we get by substituting in our numbers. So D is equal to 3,200 divided by 2.5. So what I've done here is, where I see E, I've just replaced that with the value for E here, 3,200. And where I see M, I've just replaced that with the value for M here, 2.5. Then we do our calculation, we come out with an answer of 1,280 grays. Now, technically, you would get the marks for that answer, but we've not rounded it properly, so let's just round that off properly. We find our final answer to be 1,300 grays. We know that that should be rounded to two significant figures here, because if we go back again to our question, we've got two significant figures here for mass, and we've got two significant figures here for energy. So that's what's given to us in the question, so that's what we give our final answer to. Okay, so now we've calculated part A, we're ready to go on and have a look at part B. But just before we do that, just a little reminder, these are the points where we're getting our marks. So 1 mark here for your equation, 1 mark for your substitution, and 1 mark for your final answer with units. Remember those units and make sure you've rounded it correctly as well. So part B. We're going to go for our shopping list again. So let's just have a look and see if there's any additional information here that we need to be aware of. We've got equivalent dose in the question for part B, and then obviously our answer from the last part is the absorbed dose. So let's note those down, the absorbed dose and the equivalent dose. Now, is there anything else? We need something else here. It's not giving us a value for the radiation weighting factor, but it has told us that it's alpha particles. If you remember back a couple of slides, we said that alpha particles had a radiation weighting factor of 20. Now, I can just pop that straight in here now then. So alpha particles, and it's a radiation weighting factor of 20. Now, if you find yourself sitting there in front of a question and it doesn't give you the radiation weighting factor, but it tells you the type of particle, what you can quite often do is go and look at your data sheet at the front of the question booklet or the test or wherever you're doing this, and that actually has a set of radiation weighting factors for some common quantities, common types of radiation. So let's put down our first mark now. Our equation, H equals D times WR, so that's the equivalent dose is equal to the absorbed dose times the radiation weighting factor. Plug in our numbers for our second mark, so H is equal to 1,300 multiplied by 20, and finally our answer, H is equal to 26,000 sieverts. So just a quick look again to see where we're getting those marks. 1 mark there for the equation, 1 mark for the substitution, and 1 mark for our final answer with the units. Now, we're quite fortunate this time, our units came out here to two significant figures, which is the same as what we were given in all this information that we've been given here. So we can just keep that as two significant figures. So equivalent dose rate then, what was that? I mentioned that way back at the start. We were going to look at this concept of equivalent dose rate. Equivalent dose rate is basically just the equivalent dose per unit of time. So it's how much of that harmful radiation has been absorbed over time, but it's also taking into account the harmfulness of the radiation. So this is a rare occasion, it's just important to point out, this is a rare occasion where you don't need to convert to seconds. Normally in physics we always say if you're working with time, convert to seconds. This is one of a very few, very rare occasions where you don't have to convert to seconds. You can keep your time in whatever it's been measured in. So if you measure in hours, you can keep it as hours, you can keep it as seconds, you can keep it as days, you can keep it as milliseconds, you can keep it as years. It's just depends what it's measured in, and I would just personally leave it as it is, because you don't need to, unless I ask you to, you don't need to convert that to 2 seconds in this case. The units, of course, then are going to depend on what time you've used, or what units you've used for time to start with. So, for example, if you've used seconds, if you've measured your time in seconds, your units will be sieverts per second. If you've measured your units of time in hours, then it would be sieverts per hour. If you've measured it in minutes, it would be sieverts per minute, and so on and so forth. It's fairly simple. It just means you just keep the same units that you had your time in initially. So our equation then for equivalent dose rate, this little figure, this little guy here, H dot, see the dot above here is very important, H dot, this means equivalent dose rate, okay, that little dot above just means rate. It's a mathematical term. So this is equivalent dose rate, and I've just used sieverts per hour as an example here. That could be, as I said before, sieverts per second, sieverts per minute, sieverts per year, whatever you've measured your time in. Here we've got our equivalent dose. This is what we've calculated in the first part of this lesson here, measured in sieverts. And of course we've got our time here. I've just kept this as hours just to keep it matching up with what I gave in the example for the equivalent dose rate. However, that could be seconds, it could be minutes, it could be years, could be milliseconds, whatever you've measured it in, that's absolutely fine. We don't need to convert it just for this example. Every other example you're going to come across, more than likely you're going to have to convert that to seconds. So, worked example 2 then. Let's think back to work example 1. If the sample was exposed, this is our tissue sample, if it was exposed to the alpha particles for 5.3 hours, what is the equivalent dose rate? As always, we start off with a shopping list, okay? So we're going to put down our shopping list. Let's just have a look at our question and see what useful information is here. Well, we've got 5.3 hours, that's a time. Okay, so we can note that down. Now we're going to need some more information. We're going to bring forward some information from the question. I'm just going to give that to you just for ease. So remember, we calculated our equivalent dose rate was 26,000 sieverts. And of course, we're looking to calculate our equivalent dose rate. So the first thing, or the next thing we're going to do is plug in our equation. So H dot, or equivalent dose rate, is equal to the equivalent dose divided by time. That gets you your first mark. Then we're going to substitute in our numbers for our second mark. So H dot equals 26,000 divided by 5.3. So the equivalent dose rate is equal to 26,000 divided by 5.3. Then we're going to write down our answer. Now this is a big long answer that gave me in the calculator, so I'll just put down some of the numbers there and some dots just to signify that that wasn't all the numbers that came out the calculator. I've not done any rounding here. Of course, we're going to have to round that. If we were to put that down as our final answer, we're going to lose marks for giving too many significant figures. So how many significant figures are we going to go with? Well, let's look back to our question. We're given 2 significant figures here. We've got 2 significant figures here. All the parts of worked example 1 were given to 2 significant figures. So we'll give our answer to 2 significant figures as well. So we can say the equivalent dose rate is equal to 4,900 sieverts per hour. Now notice that's per hour. I've left that as hours here because that was given to me in hours in the question. And it's as simple as that. So now what I'm going to get you to do, I'm going to get you to go away and have a look at some questions. Let's just remind ourselves of where we're getting our marks here. H dot equals H over T. So you've got your equation there for your first mark, your substitution for your second, and of course your final answer rounded correctly and with the correct units for your last mark. Right, so some practice problems. I'd like you to go away and have a look at the Waves and Radiation question booklet, page 34. You're looking at questions 6B and 6C. You did A yesterday, and then questions 9 to 18. Okay, now remember to check your answers as you're going. Don't wait till the end. Check them as you're going through it. Make sure you're getting them right, and make sure you ask any questions if you're unsure. What I will say about question 6, just while we're here, you've also got that table in question 6. Last time I said to you to ignore the last couple of columns which had the type of radiation and radiation weighting factor and equivalent dose. I would like for you to now go back and fill in those columns. Okay, so you need to look back at what you did in the previous day's work. Okay, so finally, just to recap our success criteria for today. Hopefully you can all do this now. If you can't, remember, go back. You can go back and watch this video again. You can ask questions on the Google Classroom. Just pop a comment in. You should be able to send an email via the link in Google Classrooms as well to me. So if you're unsure about any of these, just go back and either rewatch or ask questions, and I'll be more than happy to help. So I can define the term equivalent dose. I can state the relationship linking absorbed dose to equivalent dose. I can solve problems involving equivalent dose, and I can solve problems relating to equivalent dose rate. So hopefully you can do all that now. If you can't, as I've said many times now, ask questions, go back and watch the video again if you need to. That's the beauty of having a video here. You can go back and watch it again and again and again. And you maybe pick up different things each time, and that'll just kind of help you out, or ask questions. I'm more than happy to help out as much as I can. What I'll probably do is I will probably also put up some suggested past papers or past paper questions that you can try along with these, now that we have covered basically all the main equations that we need for radiation. There's one more calculation that we'll need to do for radioactivity. However, we can now go away and start looking at some past paper questions. So what I'll probably do is put on Google Classroom a couple of past paper questions for you to have a go at as well. And that way that'll just test to make sure that your understanding and your application of what we just learned is up to the standard that's going to be expected of you in any assessments that you do in the future. Okay, so remember, ask questions if you're struggling. Let me know how you're getting on. Make sure you post a comment just to let me know that you've gotten okay, or whether you've not gotten okay, what you've struggled with, or you send it via email. If you prefer not to put a comment in, that's absolutely fine. Just click on the link in Google Classroom, you'll be able to send me an email. Okay, best of luck, and I shall see you later.